So we have one more function we have to consider. This is going to be our last inverse function, inverse trig function. We're going to work with tangent, so let's think about the regular tangent function. Its graph is messy because there are all these vertical asymptotes, right? And so the domain is complicated because there are all these x values that need to be removed from the domain. And the range is kind of unique because the range consists of all real numbers, unlike sine and cosine that have a very restricted range. So as is, tangent is not a one-to-one function. We need to restrict the domain if we're going to try to define a one-to-one function. And the thinking, once again, is to try to keep the y-intercept point. So we want to try to keep this 0 point in our restriction. And in order to keep one-to-oneness, it turns out we can move both to the right and to the left of the 0, 0 point, kind of like with sine. This is very similar to the interval we found for inverse sine, because we can just keep moving to the right, keep moving to the left. In fact, we can take this sort of obvious choice of one full branch of the tangent function between two vertical asymptotes, and the function is one-to-one on that stretch. If we try to move beyond this to any other branch, we'll lose that one-to-oneness. So this is it. We just take one branch from negative pi over 2 to pi over 2. So let's draw that here. I'm going to indicate that restriction. And I want my vertical asymptotes to help me draw the graph. So I'm going to rise up to the right, come back down to the left like so, and let's see, we restrict the domain of f of x equals tan x to the interval from minus pi over 2 to pi over 2. This is a little bit different from sine because we cannot include the endpoints. We have to write parentheses. And because of the vertical asymptotes, the function is not defined at negative pi over 2 and pi over 2. It's kind of nice to have this simple domain as opposed to the official domain of the domain of the entire tangent function. So there's something nice about this, that we're getting a simpler interval for our domain. The range is still the interval from minus infinity to infinity, all real numbers. And so now we have a one-to-one function. And we can define f inverse. And let's go ahead and do that. So here I just redrew what we just did. I have that ready here. So there's our portion of the tangent with the restricted domain. Now we want to obtain the graph of the inverse function. And so this will be our graph of f inverse of x, which is tan inverse of x. And so a couple interesting things. We got 0, 0. The values on the horizontal axis become values on the vertical axis. I'm going to label pi over 2 negative pi over 2. Now these asymptotes transfer over to the inverse function. And because we're interchanging x and y, because we're interchanging the axes, can you see that the vertical asymptotes are going to become horizontal asymptotes on the graph of the inverse? So we actually have these two horizontal asymptotes. And there aren't too many examples in math that you see the functions with two horizontal asymptotes. Now, I'm not going to ask you to always label the pi over 4 points, but just notice we have pi over 4, 1 is a point on the graph of the restricted tangent. So 1 pi over 4 would be a point on the graph of the inverse function. So the first coordinate's 1, second coordinate's pi over 4. And we're going to get a curve something like so. Just like we have negative pi over 4, negative 1 on the graph of the restricted graph of tangent that we're using, then I will have negative 1, negative pi over 4, which is going to be here. And I'm going to approach that horizontal asymptote in that direction. So it's like one horizontal asymptote applies to one direction, pi over 2 for the positive direction, and negative pi over 2, the lower horizontal asymptote applies for the negative direction. And so just notice this point we would say has coordinates negative 1, negative pi over 4. So for our inverse, the domain is the range of the restricted function. The domain is all real numbers. This is actually the one case where I feel the inverse function has a nicer graph than the original function. I wouldn't say that for sine or cosine. The range of the inverse is the interval from negative pi over 2 to pi over 2 with the endpoints not included, because it never hits those y values at pi over 2 or negative pi over 2. Tan inverse x is also written arc tan x, which you'll see in some other books. Tan inverse x does not mean 1 over tan x, just like with inverse sine and cosine. And tan, whoops, sorry, I'm going off the bottom of my sheet here. Tan inverse A equals B means tan B is A and B is in that interval from negative pi over 2 to pi over 2 without those endpoint values included. All right, so let's start doing a couple problems. And I just want to use this sheet where we got some of our defining relationship about inverse tangent up at the top. And let's do some exercises, some problems. So the first one is, let's find tan inverse of 1. Now it's actually on the graphs I was drawing, so we We could just look at our graph. I guess I'll write out the details here. This again, I just want to remind you, like I did with inverse sine and cosine, the role of B here and here is like an angle. Just like the input for the tangent we think of as an angle, the output for the inverse tangent is an angle. So I can call this theta. We're looking for an angle value. Let theta equal tan inverse of 1. Then tangent of theta is 1, and theta is between negative pi over 2 and pi over 2. Now, sometimes that interval will be essential for us to note. Sometimes it won't be so essential. Here, whether we look at our graph of tangent or inverse tangent, we know tangent of pi over 4 is 1, so theta is pi over 4, or 45 degrees. Tan inverse of 1 is pi over 4. Number 2, find tan of cosine inverse of 1/2. So we have one of these composition situations. In this case, I want to give a name to the output of the inverse cosine. We've done this in a couple problems now. So I'm going to let theta equal cosine inverse of 1/2. And what we want to find for our answer is actually going to be tangent of theta, tangent of that angle. Let's see if we can figure out what theta is. Cosine theta. Cosine theta is 1/2. And what interval does theta have to be in? It's coming out of the inverse cosine, so we have to go back to that 0 to pi interval. That's tied to the definition of inverse cosine. Here it's not so crucial because I think there's one obvious value for us to pick here. We know, let's see, cosine is 1/2. That's at 60 degrees or pi over 3 radians. So theta is pi over 3. So tangent of cosine inverse of 1/2 is tangent of cosine inverse of 1/2 is our theta value, pi over 3. That's just tangent of pi over 3. Oh, well, that's sine of pi over 3 over cosine of pi over 3. This is just a good old-fashioned problem from earlier in the course now, once we get beyond that inverse cosine step. And let's see, sine of pi over 3 is square root of 3 over 2 over cosine of pi over 3 is 1/2. We're just using that fact that we've already seen in this problem. And so I get square root of 3 over 2 over 1/2. When I divide that out, is square root of 3. There's my answer for number 2. Tangent of cosine inverse of 1/2 is square root of 3. I got one more here in this portion of in this video. We're going to do tan inverse of cosine of pi over 3. Playing a little bit of games with that notation maybe here. Now, this idea of calling something theta, right? This makes no sense as theta. The output of cosine isn't an angle. The angle's already in there. I can see calling the whole quantity theta because that's the output of an inverse function. Let theta equal tan inverse of cosine of pi over 3. Then tangent of theta is equal to cosine of pi over 3. Oh. Tangent of theta is cosine of pi over 3 is actually cosine of pi over 3 is 1/2, right? And now we need to find an angle whose tangent is 1/2, and